Oh, sorry. Today's talk is going to be about the uncertain future of the Antarctic ice sheet. I'm going to talk about the importance of quantifying uncertainties in ice sheet model projection. So this presentation is more about what I did during my PhD, but there's a few slides on what I'm currently doing here at JPL, but this is still a work in progress. So let's start now. I'm going to start with basically this sentence from the special report of the IPCC in 2019, basically saying that right now we've got a better understanding of the ice sheet dynamics since RF5, but on the other hand, there is deep uncertainty regarding ice sheet projection, especially for Antarctica. And what do we mean with deep uncertainty? It means that we've got a complex system with a lot of complex input and a lot of complex output. So everything I would say in the system is globally uncertain. And the uncertainty, this kind of deep uncertainty, especially arises beyond the 21st century because a lot of models lack the kind of realistic representation, for example, to model ground line migration or sliding. So let's have a look at this picture. So these are basically the new IPCC projection for the evolution of sea level. So what we can see basically is that there is a big uncertainty for the Antarctic ice sheet contribution, especially after beyond 2100. And these new results are quite interesting because they're totally different from the results that we had in RF5. Because in RF5, basically the conclusions were that the contribution of the Antarctic ice sheet to sea level would only be very small. But the problem was that at this time, I would say that ice sheet models weren't really capable of reproducing instability mechanism in their ice sheet model. But right now, we're pretty sure that the contribution is going to be positive and can be quite high, especially in the next centuries. So here, just for those of you who are not very familiar with ice sheet and glaciology, so here we've got a map of the bed elevation in Antarctica, and what we can see is that there are some places where the bedrock is basically below sea level, and it can be very deep below sea level, especially in West Antarctica, but also in some basins in East Antarctica, like the Wilkes Basin or the Aurora Basin. And why are the regions very important? Because the net mass loss of the Antarctic ice sheet will be dictated by the response of the marine sectors in Antarctica. And why this is the case? Because a few years ago, people realized, especially in a theoretical way, that there could be instability mechanisms that can lead to a very rapid collapse of these marine sectors, especially in West Antarctica, for example, for thread glaciers, but also in some basins in East Antarctica. So one of these instability mechanisms is the marine ice sheet instability, the MESI mechanism. And the basic idea behind this mechanism is that if we have the grounding line, so the transition line between the floating ice and the grounding ice, then this grounding line can basically be unstable if it lies on a bedrock which has a retrograde flow. And I just would like to mention that there are also other instability mechanisms like the marine ice cliff instability mechanism, but this mechanism is not really well understood and we're not really sure if it can really happen in the future for Antarctica. So I prefer only to focus on the marine ice sheet instability. So if we want to make a sea level rise projection, then we need an ice sheet model, and here is, I would say, a schematic view of an ice sheet model. So the idea is the following. we've got a set of input variables, and for example, the bedrock elevation, the surface temperature. We've got our ice sheet model here. This is simply a simple view of an ice sheet model, but you've got to be aware that this kind of model can be very, very complex. We've got to solve basically differential equations for the ice flow or the interaction between the ice and the bedrock or the ice and the ocean. And we've got a lot of outputs, for example, the change in volume, the change in area, or the ice thickness. And I would like to mention that the input variables as well as the output variables can be very complex. They can be, for example, only scalars, but they can be also quantities that vary in space and also in time. For example, the bedrock elevation or the surface accumulation. So in my case, I will not really focus on the model, but I will consider it as a black box model, and we will really consider the ice sheet model as a way to map the input variable into some quantity of interest. And what really interests me is that the fact that we can consider uncertainty in all these input variables and also in the model in itself. And we want to know all these uncertainties can translate into uncertainty in the output variables. So this slide is a bit of a summary of what I just told you. We've got in an ice sheet model different kind of uncertainty. I would say we can have some kind of we can have different kind of categories. First, we can consider what I would call intrinsic variability, intrinsic uncertainty. This is basically the kind of uncertainty that you cannot reduce. If you just consider the surface, the atmospheric forcing, there is an intrinsic variability. And this one, even with super powerful model, you cannot reduce it at some point. And there are also noisy data, for example, the bedrock topography, the ocean temperature, or also some kind of quantity that you've got to infer in an indirect way, for example, the basal friction coefficient. The other type of uncertainty I'd like to mention are the modeling error or the structural uncertainties. These are basically the fact that models are at some point uncertain. For example, there are uncertainties in the way that we model friction at the ice base, the way that we model the bedrock response, or also all the interaction between the ocean and the ice. There is also the problem of the initialization, because usually we use the initialization to infer for the friction coefficient, but there are different ways to do it, for example, using spin-up method or inverse Froment. And of course, there are all these numerical errors due to the discretization or also numerical noise. And usually, I would say that structural uncertainties are much more difficult to quantify than uncertainties due to input parameters, because we do not have really something that we can measure. So the best way so far to quantify the structural uncertainty is by doing so-called multi-model ensembles. For example, all these intercomparison project that Frank, for example, talked about a few weeks ago, or also this kind of project like the CRISE project or the ongoing ISMIP6 project. And the last source of uncertainty that I want to mention are all the parametric uncertainty that we can find in the models. For example, if we think about the rheology of the ice, we've got this Glen's rheological exponent, and this one we can consider it to be uncertain, or for example, a parameter in a sliding load. So let's go now to the outline of the talk. So I did the introduction. The next slides are going to be more technical one. I'm going to discuss what are the challenges associated with uncertainty quantification with ice sheet model. And in the second part of the talk, I'm going to show you an application. So Let's start with a brief overview of uncertain quantification. So how does it work? So basically, first we can consider that we've got a bunch of uncertain parameters or uncertain quantities of interest. The first step that we've got to do is basically to model the uncertainty in these input variables. And it's not always done properly, but this step is really critical, especially because we can have very, very complex input parameters. In the case that we've got only scalar parameters, it can be pretty easy to do it, but usually we can have quantities of interest that vary in space and in time. And in this case, traditional methods are not very useful. And later in this talk, I will discuss a little bit about how we can, for example, model uncertainties in quantities that varies in space and in time. But for now, we can simply consider that we've got only a single parameter x that is basically uncertain. So the next step that we've got to do is then to see how the uncertainty in the input variable translates into uncertainty in the output variable, for example, in sea level. And to do it, we're going to use the computational. And so we have what we call the propagation of uncertainty. So the idea is basically, can we transform uncertainty in the input variable into uncertainty in the output variable? It is really what interested us. And the next step is what we call a sensitivity analysis. This is relevant when we've got several inputs, and the idea is simply to see which are the most influential parameters in inducing uncertainty in the output variable. And when, for example, here we can see that x1 is the greatest influence, and it can really help the iSheet modeler, for example, to see where we've got to do efforts from an observational point of view in order to reduce the uncertainty in the input variables. So now I'm going to discuss how we can do the propagation of uncertainty. One of the most straightforward approach is the Monte Carlo approach. The idea is the following. So here I'm going to consider that I've got two input parameters, and I'm interested in projecting the contribution of the Antarctic ice sheet to global mean sea level. So to do Monte Carlo sampling, it's really straightforward. The idea is simply to sample point in the parameter space in a probabilistic way. So here we've got a lot of these points that are drawn randomly in this parameter space. And for each of these samples, we basically run the model and we obtain a projection for the increase in sea level. And so when running the model for a large ensemble of Monte Carlo samples, we can have a pretty good estimate of the global mean sea level rise. The only problem with Monte Carlo sampling is that usually this method can be quite slow to converge. We usually need a lot of samples to obtain a reasonable estimates of the quantity of interest. So an idea is to, rather than using the computational model to obtain the projection, because really the bottleneck here can be the computational cost of this model. For example, if we just think about an iSheet model, it can take a few hours or even a few days to obtain just one single run, and it can be prohibitive to do uncertainty quantification. So rather than using the computational model, what we can do is to build what we call a surrogate model, but also other people call it an emulator. The idea is to obtain an approximation of the computational model from a few samples in the parameter space, and these samples are chosen in a careful way. And once we've got this surrogate model, we can simply run the Monte Carlo analysis using the surrogate model instead of the computational model. And this kind of approach can really reduce the computational cost of the uncertain quantification analysis. Here, I just want to mention two popular surrogate models. So the first one is what we call polynomial chaos expansion. The idea is basically the following. So we've got here our true model in the blue, and we're going to build an approximation of this model by considering an expansion of the function f of x using a polynomial basis. In this case, the polynomial basis is assumed to be orthogonal in a probabilistic sense. And another way of building an emulator is by using Gaussian process regression. The idea is the following: we assume that the true model is a realization of a Gaussian process, and from a few observations, so the red dots, we're gonna try to find an approximation of this model. And the idea is the following: as we are working with Gaussian process, the best estimate, so the red line, is given by the conditional expectation of the Gaussian process given the observations. And the nice thing with Gaussian process regression is that we can also have a measure of the uncertainty in the red line. So here, the shaded area is basically the uncertainty in the projection. And in this line, I'm going to just talk a little bit about sensitivity indices. There are different ways to do sensitivity analysis. Here, I'm going to consider what we call global sensitivity analysis. And the idea is the following. So we have a model, and we're going to decompose this model in this way. So here we've got simply a constant function. And here we consider a sum of functions that only depend on one of the parameters. And the last function is what we call an interaction effect. And why this is interesting, this decomposition, because it really helps to separate the effect of all the parameters independently. And just for details, so the expression of these functions are given by this expression. These are, so if you're not really familiar with mathematics, you just have to think that this function is simply the mean value of the quantity of interest when we fix the parameter xy. So this is where we've got here the conditional expectation. And once we consider this decomposition, what we can do is simply to take the variance of this decomposition, and we can see that we can decompose the variance of the quantity of interest as a sum of different contributions. So these SI are basically called sensitivity index or Sobol index. And why are these indices very interesting? Because they globally quantify the contribution of each input parameter to the global variance. So the higher these indices are, the higher the contribution of the parameter is to the global variance. And how we can estimate these indices, it can be done using Monte Carlo estimation or also using surrogate model. So the next step, so this was an overview of UQ method. Now I'm going to discuss a little bit on how we can quantify uncertainty in the retreat of the ice sheet. So here you can see different maps. And what we want to do is to see how can we quantify in a probabilistic way the retreat of the Antarctic ice sheet. And it can be very complex because Previously, I was assuming that basically the quantity of interest is just a scalar. For example, the global mean sea level. Here, we've got to deal with something that is spatially distributed. And to represent the uncertainty, it can be a bit more tricky because we cannot simply compute. Yeah, we could compute the mean value, but it does not give us an overview of the whole uncertainty. So what we were interested to do is the following. If we consider two runs of our model, so here you can see the granite ice area and here. And these are for two sets of parameters. So here we can definitely see that most of West Antarctica has disappeared. And here I would say that the whole Antarctic ice sheet is basically the same. And I would define this region, the yellow region, simply as the region where the ice is grounded. And if we use a little bit of mathematics, we can simply use Archimedes' principle just to see that this region is simply the set of locations where this quantity, the height above flotation, is above 0. So from a mathematical point of view, I'm going to be a little bit general and call this set an excursion set. So this is basically the set of locations where a quantity of interest, for example, the height above flotation, is above some thresholds. Here, the threshold U is simply equal to 0, but it can be another value. And what we want to do is to characterize the uncertainty in this random closed set. So to do it, let's have a look at these few pictures. So I'm going to say that this set here is the yellow egg. And to represent the uncertainty in this yellow egg, I'm going to consider here this red egg. And I'm going to call this red egg an inner confidence set. If there is some probability level, then the red egg is inside, is within the yellow red. And we can do the same and consider a green egg that is called outer confidence set. And this is an outer confidence set if the probability that the yellow egg is within this green egg is some level of probability. So I will not really go into the details on how we can compute these confidence set. The idea is just to understand the definition, to really see that the way that we have defined these confidence set is really useful to represent the uncertainty in a quantity that varies in space. And for those of you who are interested, so basically the idea to compute these confidence set is simply to consider a parametric family of confidence sets. And basically we're gonna solve an optimization problem to find a value for a threshold such as a T row satisfies the desired level of probability. So next, here I talk about uncertainty in the output, in the input output quantity, uncertainties in the output quantity that can vary in space. And now I'm going to see how we can model uncertainty in a quantity that can vary, in an input quantity that can vary in space, but also in time. So for example, if you just think about the surface mass balance, it typically varies in space, but also in time. And one way to represent this uncertainty is to, for example, model the uncertainty as a Gaussian random field. So what is a Gaussian random field? This is basically a function where at each location we've got a Gaussian variable, and there are some correlations between the different points. And without going into the detail, actually, here we're going to consider a special class of Gaussian processes with what we call the Mattern covariance function. And what we are interested is to generate realizations of this Gaussian field. And one way, a practical way to do this is by solving a stochastic partial differential equation. So here we've got a differential equation, but the right-hand side is random. And to model quantities that vary in time, one way of doing this is by considering a first-order autoregressive model. So the idea is pretty simple. If we consider the variable at time t, we can say that it's the variable at time t minus 1 times a temporal correlation factor, and we add noise, and the noise is computed following this approach. And just to give you an idea of how this approach can be used, so here I generated a few samples for Pine Island Glacier, and we've got realizations of our Gaussian field, but for different correlation lengths. So here we've got 10 kilometers, 50, and 100 kilometers. And what we can see is by basically tuning this scaling parameter, we can increase or decrease the correlation length between locations. And it can be very useful to model different kind of processes that can have different correlations length. So this slide basically ends, I would say, the technical part of the talk. And now I'm gonna go into the application, which is how we can use all these technical methods to make projections for the Antarctic ice sheet. So here as an illustration, so we've got two runs of our models for different kind of parameters. And this is just to illustrate that parameters can really have a big influence on the results. So here we can really see that for this set of parameters, there is only a limited retreat of the grounding line, but on the other end, for another set of parameters, we really have a big retreat of the grounding line, especially in West Antarctica, where we have a major collapse. So what are the simulations that we perform? So we try to predict the contribution of the Antarctic ice sheet to sea level rise over the next millennium under the 4 RCP scenarios, as you can see there. And I use the fetish model that is developed in Brussels by Frank Patin. And we force the model with different kind of forcing. For first surface temperature forcing in this way. The model is also forced by the ocean using a coupling, a simple coupling between ocean temperature and subshelf melting. And we consider different kind of sliding laws. Here, the sliding law that I'm using is a power law sliding law, the Weightman sliding law, with different kind of exponents. So the nominal value is here m equal 2, but as a comparison, I'm also consider the case where m equal 1. This is basically a linear sliding law, or m equal 3 that represents a more strongly nonlinear sliding law. And the ground line migration is parameterized using Schuf's ground line flux condition. So this is basically a theoretical value which gives the value of the flux at the ground line, and this theoretical value can be used to model the ground line migration. So here, how do we introduce uncertainty in the model? We do it in this way. So we consider uncertainties in a few parameters. I will not go into the details, but you just have to consider that we have uncertainty in the calving rate. So this is modeled using this F-calv factor. We also consider uncertainty in the ocean temperature to represent uncertainty in the ocean forcing. This is this F melt factor. We also consider uncertainty in the rheology of the ice shelf. So basically, we can consider that the ice shelf is more viscous than the ice in the grounded part. And to make ice more viscous, we introduce shelf tuning factor. And we also consider uncertainty in the relaxation of the bedrock, basically for West Antarctica and for East Antarctica. And the value for East Antarctica is higher than West Antarctica because West Antarctica is a faster relaxation time than East Antarctica. And also we consider uncertainty in the sliding law by considering different kind of exponent, 1, 2, and 3. So what we did to make our projections, we used an emulator. In my case, I used a polynomial chaos expansion. And basically, we use a bunch of 500 training samples. And just to give you an idea, just running these 500 training samples amounts to approximately 50,000 hours of computational time. So this is why using a surrogate model can really decrease the computational cost, because if we had used Monte Carlo sampling, the computational cost would have been definitely much, much higher. And so let's go to the projections now. So first, I'm going to start with the nominal projection. So the nominal projection are basically obtained for these values of the parameters. What we can see is that for the first decades, there are only a limited contribution to sea level rise. And the contribution starts to increase much more significantly around 10,000 per 100 with a rather constant growth rate. And as you can see, the contribution in our simulation is only significant by 3,000 for RCP 8.5 with a contribution of around 4 meters. And for the other RCP scenario, the contribution is less than a meter. So why is an emulator useful? First, we can use it to obtain an idea of the relationship between the input parameters and the quantity of interest. And what we can see here, so this is the emulator for each of the input parameters. So basically here I'm varying one of the parameters and the other parameters are fixed at the nominal value. And we can see that there is a nonlinear response with response to the carving factor and also the shelf enhancement factor for RCP 2.6. For the F-melt factor, the relationship is pretty well linear. And what we can also see is that in our case, the bedrock relaxation types do not seem to contribute significantly to the projections. I did the same figure for RCP 8.5. And in this case, we can see that things are a bit different. Especially, we've got a nonlinear response this time with respect to the melt factor. And this kind of response can be explained by the collapse of the West Antarctic ice sheet. Once the West Antarctic ice sheet is collapsed, we reach some kind of plateau, and then for higher forcing, we start to trigger the retreat of East Antarctica, and that's why we've got here an increase in a global mean sea level rise for higher values of the melt factor. And definitely what we can see in this in these 5 figures is that for RCP 8.5, the response of the Antarctic ice sheet is definitely controlled by subshelf melting. And now these are our projections. So here the curves represent the medium projections, and these shaded area are basically the 33 to 66% probability intervals. So what we can see is that on short time scale, so before 2100, the contribution to sea level rise remains quite limited. But in warmer scenarios and on longer time scales, the contribution of the Antarctic ice sheet becomes more significant, and the impact of uncertainties also become more significant. So here we can also see that for RCP 2.6, we only have a limited contribution to sea level rise. And this conclusion is basically robust with respect to uncertainty. Oh, here it is. And these are the same projections, but this time for the linear sliding law, and this time for the more strongly nonlinear sliding law. And what we can see is that more nonlinear sliding conditions will favor a more significant ice loss. And now let's have a look at the probability distributions for sea level rise by 2100 and 3000. What we can see is that for both times, all the probability distributions are basically unimodals. But if we consider the time 3000, we can also see that especially for RCP 8.5, we've got a super large tail. And in RCP 2.6, the distributions are globally Gaussian shaped. But for RCP 8.5, we can see that the distribution is somehow flat. And by 3000, we've got a localized mode for higher values. And this kind of behavior can be explained by the relationship between the F-melt factor and the global mean sea level rise. If you remember, by 2100, the relationship was globally linear, and this may explain this kind of behavior. On the other hand, by 3000, we had this kind of plateau behavior that may explain this localized mode. And what we can see is that also by 2100, the probability of exceeding 50 centimeters of sea level is really negligible. It's less than 100%. And by 3000, the probability of exceeding 50 centimeters in RCP 2.6 is less than 30%. And on the other hand, if we consider the scenario, the RCP 8.5 scenario, the probability of exceeding 1.5 meters can reach this time more than 95%. And here, these are the same projections, but with different sliding laws. And we observe the same results as previously. In this case, we can see that more nonlinear sliding law once again favor a more significant ice loss. And now let's have a look at these sensitivity indices. So these are the results for 3 different years. And here we can see the contribution of each parameters to the uncertainty in global mean sea level rise. As you can see, if we consider RCP 2.6, we can see that the dominant source of uncertainty is the ice shelf rheology, followed by the Kelvin rate and subshelf melting. But as we consider warmer scenario, we can observe that the dominating source of uncertainty becomes the uncertainty in subshelf melting, and especially for RCP 8.5, here we can see that basically all the uncertainty can be explained by the uncertainty in subshelf melting. And you might wondering why we cannot see any purple or any green. And this is basically because the Sobol indices for these two input variables are basically negligible. And once again, it shows that in our case, the contribution of the uncertainty in the bedrock relaxation time is quite negligible. So now let's have a look at the retreat of the grounded portion of the Antarctic ice sheet. So here, these are the nominal conditions. And we can see that for RCP 2.6 and RCP 4.5, we basically have no retreat of the grounding line. If we consider this time RCP 6.0, we've got a more significant retreat of the grounding line, especially in the Rhone basin and also a little bit in Cyprus coast. And if we consider now RCP 8.5, we have this time a much more significant retreat of the ground line in the Amundsen Sea sector, but also in Cyprus coast and in the Rhone basin. So now let's see how these projections are affected by uncertainties, and we obtain these maps. So can we interpret them? But here, so what I did is basically I superimposed different confidence sets for different levels of probability. So here you can basically tell that the gray area is where we've got a probability of keeping ice with a probability level of 100%. If I consider, for example, this blue color, this represents the regions where we've got a probability of at least 50% to lose ice. And what we can see is if we add uncertainty in our model for RCP 2.6, there is basically no retreat of the grind line. So the regions in colors are really small, so the retreat of the grind line is really small too. If we consider RCP 4.5, we can see that this time there can be some retreat of the grinding line. And if we consider RCP 6.0, this time we can have a potential risk of collapse of the West Antarctic ice sheet with a probability level of 33%. And this is interesting because if we look at the nominal projection, we were basically saying, okay, there is no risk of collapse of West Antarctica. But if we consider uncertainty in our model, this time we can see that there can be a risk of major collapse of West Antarctica for RCP 6.0. And if we have a look at RCP 8.5, basically all west Antarctica is in orange. So there is a very big risk of major collapse of West Antarctica by 3000. And we can also observe some risk of retreat of the grind line in Wilkes Basin. So this really shows that the contribution of the Antarctic ice sheet to sea level rise will really be dictated by the response of the marine sectors. And let's have a look at these kind of maps for other sliding laws. So what we can see here is that with more nonlinear sliding condition, once again, we've got a bigger risk of retreat. Here, for example, if I consider the linear sliding law for RCP 8.5, we do not have super high risk of losing the whole West Antarctic ice sheet. I would say it's only 50%, but for m equal 2 and m equal 3, the risk was more than 95%. And it's still interesting to mention that for Cyprus coast, we can observe here for m equal 1 a higher risk of retreat than for m equal 3. So one of our possible explanation was due to the configuration of the bedrock in cycle cores that may explain why the retreat is more important for a linear sliding law than for a more non-linear sliding law. But usually when sliding conditions are more non-linear, we observe a higher risk of retreat. And now to finish this projection, what we also did is to change the sliding conditions at the ground line. And instead of using a Waveman sliding law near the ground line, we can consider Coulomb friction conditions at the ground line. And this leads to use the side grinding line conditions that makes projections more vulnerable to changes in environmental conditions. So here you can observe that we can have projections that can reach 9 meters of sea level rise contributions. And here for RCP 2.6, even with side condition, with side condition, this time the probability of exceeding 50 centimeters can reach more than 40%, and the probability of exceeding 1 meter can reach this time 10%. And if we think about Schuff's grand line condition, the probability of exceeding 50 centimeters was really negligible. So this really highlighted friction conditions at the grand line are really critical to make projections. And these are confidence sets for the side grand line condition. And we have the same conclusion as in the previous slide. We can see that the grand line parameterization leads to an increased grand line sensitivity to environmental changes. So, for example, for RCP 4.5, we have a major collapse of West Antarctica ongoing. And for RCP 6.0 and RCP 8.5, there is definitely a high risk of major collapse of West Antarctica. And also in RCP 8.5, for side grand line condition, we can also observe a retreat of the grand line in Wilkes Base, in Ora Basin. Sorry. And so just a few discussion of our results. So if we compare these results with other kind of projections, we can see that, for example, these projections of sea level rise are in agreement with other studies. For example, the studies of Gaussian and DeConto and Pollard for RCP 2.6. And for RCP 8.5, we are basically in agreement with Gaussian, but our projections are much less important than in DeConto and Pollard. But these projections were made assuming the marine ice cliff instability, and it's not totally, we cannot really compare our projections with these ones. And especially in this article, projections were very high. I think there are a few recent articles where these projections have been somehow revised. And if we have a look at the Granian ice retreat, we showed that the Granian line retreat was more significant in the Cyclone code, but other studies suggest that the Granian line retreat could be more significant, for example, in the emergency sector. And why this is not the case for us, it's there may be a few reasons. For example, the resolution of our model, the way that the grand line migration is represented, and also the way that ocean faulting may be applied to the grand line. And if we look at the impact of parametric uncertainty on the projection of the Antarctic ice sheet, what we basically concluded is that our projections for RCP 2.6 are pretty robust to parametric uncertainty. So we can say that for RCP 2.6, there will be no collapse of the West Antarctic ice sheet. And with a high level of confidence, we can say that the contribution to sea level rise will remain quite small. For RCP 4.5 and RCP 6.0, we can see that we showed that projections are most sensitive to parametric uncertainty. If we consider nominal projection, we basically concluded that the contribution was quite small, but if we introduce uncertainty in the model, we showed that the projections can be much higher, especially for RCP 6.0. If we looked at the nominal projection, we predicted almost no retreat of the grounding line. And if we consider uncertainty, we can see that we can have a major collapse of West Antarctica. And if we consider RCP 8.5, projection this time are also robust, but in a negative sense, I would say, because in all scenarios, for all values of the parameters, we basically project a complete collapse of West Antarctica. And to finish, let's just have a look at our projections with other kind of projections. So the projections that we did are these ones. So these are the projections with Schur's ground line migration flux. And these are the projections using size conditions. And here we've got other kind of projection, the projection by Decanto, the projection by Gaussian. There are also the projections by Leverman. And here, these kind of projections are a bit different because these are not model-based projections. These are the projections by member, but these are based on expert assessment. And these are other projections by Decanto and Porat, but this time with a bias correction for the ocean. So, and also here we've got the RR5 projections. And these are all box plots. So on the left, we've got the projection for RCP 2.6, and on the right, we've got the projection for RCP 8.5. And what we can see is that for RCP 2.6, basically all models agree on a limited median contribution to sea level rise. So it's a way to basically gauge the influence of structural uncertainty. So we predicted a limited contribution, and it looks like it's basically the same for all models. If we have a look at RCP 8.5, this time the median contribution is between a few centimeters and 20 centimeters without the marine ice cliff instability. But if we consider the marine ice cliff instability, this time we can see that the median contribution can be over 60 centimeters. And in the case of RCP RR5, I just would like to mention that the contribution ice sheet dynamical changes were basically dominated by snowfall, because RR5 in RR5 studies weren't really able to capture dynamical changes, while right now new models are more able to capture instability mechanisms and ice sheet dynamical changes. And so let's have a look at other results for 2300. And what we can see is that there is definitely a deep uncertainty in projections between 2100, especially for RCP 8.5. And we can see that for RCP 2.6, most models basically agree on a median contribution below 50 centimeters. And for RCP 8.5, all models agree on a median contribution above a meter, but there is definitely large differences in the magnitude of this contribution between models, even between models which do not consider the Mickey mechanism. And to finish, just a few perspectives. So as we So yeah, there is a big room for improvement in ice sheet projection and the way that we can incorporate uncertainties in them. One way to improve projection would be, of course, to improve ice sheet models. I would say to improve initialization schemes, but also to improve the coupling with other system components. Of course, data sets are always super useful to constrain parameters. Other type of UQ methods could be used, for example, machine learning algorithm, and also methods to improve the characterization of uncertainty, for example, Bayesian inference or spatial temporal models, and also methods to quantify and to gauge the stability of ice sheets with in the presence of uncertainties. So I think I'm gonna finish here, and I thank you for your attention.
Thank you very much, Kevin. That was a fascinating talk. Perhaps I should get some canned clapping. It might suit these endings. So we have a couple of questions in the chat. So the first one was from Andreas. Andreas, would you like to unmute perchance?
Sure. Can you hear me?
Yeah, sounds good.
Hi, thanks for the very nice presentation. I was just wondering if your simulations include the sea level effect themselves on the behavior of the Antarctic ice sheet.
Unfortunately not, but definitely it should be taken into account.
How would that affect your results?
Probably it would lead to increased stability. So I would say it would decrease the projections. Maybe it would make some scenarios more stable. For example, RCP 4.5 and 6.0. They are especially these ones because they really look like they're very vulnerable to uncertainty. So maybe including change in sea level would make them more stable than I predicted.
Why do you think that? I had the opposite idea that sea level rise would lead to destabilization of the ice shelves and the grounding line, but maybe I'm wrong.
Maybe I'm wrong too. No, if we maybe normally if we increase sea level, it would make oh yeah, it would. Does it? I can't remember. Does it make it more stable or not? I would say.
I would have thought it would have made it less stable, right? If you're increasing the level of the ocean.
Mm-hmm.
But it's a small rise.
Yeah, but yeah, definitely for RCP or 2.6, this should be quite negligible. But for RCP 8.5, it should have an effect. So.
Okay.
Yeah, it's a fascinating question. Sorry to interrupt you, Andreas. Okay. So we have another question from, we've got a question from Vivian. Vivian, is there any chance you'd like to unmute and say hi?
Yes, I mean, this is coming from someone with limited statistical knowledge. I'm just curious, how much more accurate representation of uncertainty do you have in using this very advanced statistical mathematical methods that you discussed earlier in the talk, as compared to more standard statistical approaches. And then the second part of the question is, wouldn't it be more important to focus on developing more, physical models of ice dynamics, for example, that more realistically portray what's happening in nature?
Definitely, yeah. For the second question, I would say both are complementary because, of course, yeah, one way to increase robustness in the projection is definitely to improve the physical representation of models. So, but in any case, I think you would have to introduce or to consider uncertainty in some way or another, even if your model is more accurate. So I think that both are complementary, but they're definitely just focusing on statistical method does not make any sense. Because yeah, the results they do not have any, yeah, they've got physical interpretation, but definitely a physical model would give more physical insight. So I think that both are useful. And for the first part, why are these methods more useful than traditional statistical methods? Yeah, do you have anything in mind when you talk about traditional statistical method?
Well, whatever the standard methods that are widely used.
I say, yeah, the standard method would be simply, yeah, to compute a mean value or a standard deviation. In this case, you can really have a global representation of the whole probability distribution of your input or output quantity, especially if you want to study the extreme cases. Or more traditional method would only give a rough estimate. And of course, yeah, traditional method could be useful. I think that the method that we use also provide another way to see the impact of uncertainties. And I wouldn't say that they are better, but they are definitely complementary. And yeah, I don't know if it's really answer your question.
Yeah.
Thanks, Vivian. There's a conversation going on in the chat between Frank and Andreas, which is quite nice. So they're talking about the impact of sea level rise on the stability of the ice sheet. And I believe Frank is making the point that, as WAIS loses, the West Antarctic ice sheet loses mass, you might expect to see a fall in sea level rise close to the ice sheet due to changes in the geoid. I believe that's correct. If you look at the recent trends in sea surface height around Antarctica, rather interestingly, there is a rise for the majority of the continental shelf, but there is a rather dramatic fall, particularly in the last 5 years or 10 years around West Antarctica sheet, which is fascinating. I don't know if anyone has done sort of like long-term modeling studies where they looked at the impact of sea level rise and including all the various components on the stability of the ice sheet out to something like, I don't know, 2100, 2300. I think that would be fascinating to do. I think there are lots of components that we should think about. Hey, Frank.
Well, Craig, yeah. So that is, I pointed you to Violaine, and that's a bit what her paper is about.
Yeah, but no, definitely increased sea level rise would destabilize because the ground line would be deeper.
Is Violaine on the chat, perhaps? It'd be interesting to talk to her.
Yes, she is.
It'd be interesting to know what components she's included within that study, because as Andreas points out, I think there are multiple components, and I think there's going to be regional variability.
Yes, but she only looked at the local, so the effect of mass loss on Antarctica on the Antarctic ice sheet, so not the global geo changes. So not a global full self-gravitational effects on the whole globe. So that means it doesn't take into account mass loss from the Greenland ice sheet, for instance, which Andreas pointed to. But it's interesting to see if you look at different viscosities of the mantle, for instance. That gives already quite some different responses.
Yeah, it sounds fascinating. It'd be great to have her speak and to hear about her work. Sorry, Kevin, that thread took over a little bit. Do we have any other questions from the group, from anyone? We have a comment from Andreas again about he believes Natalia Gomez did some interesting projections for sea level effects. Okie doke. We're a little bit over time here. We have people leaving the group. We have another question for Vivian. Vivian, would you like to unmute the chance?
This was simply in response to the conversation about, what is the effect of the melt, the retreat on the ice sheet, and will it contribute to sea level or not? And I would think that it depends on the relative rates of the glacier, the ice shelf thinning and glacier advance versus the isostatic rebound and the the weakening of the gravitational attraction. So it's sort of competing forces going in different directions. So it depends on the net effect, I would think.
Yes, yeah, it's a fascinating problem. I'm not sure. I should look up, see if anyone's done that work to look at all the various components and how they compete. Okie doke. Do we have any final questions, comments, final statements? We're a little bit over time. We should probably let people get on with whatever. Next, we have a couple of comments. Thank you from Frank. Thank you from Victoria. Okie doke. Thanks ever so much, Kevin, for a fascinating talk. I look forward to uploading this one and adding it to the body of work on the YouTube. Yeah, thanks again. I hope everyone has a great rest of the day, and we will see you next week. Cheers all, thanks.